All right, everybody, let's get started. I'm recording this video Monday evening in advance of our lecture on Friday. As I mentioned in class on Monday, we're not going to be having class on Friday because of our college level meeting, and so I needed to pre-record this lecture. However, if there's any lecture I'm going to pre-record, I think this is the one that makes quite a bit of sense to do it. Especially given the troubles that we've had with the manual, because this is one that you can sort of watch, I guess I should say, once your manual comes in, this is something that you can catch up on and do the associated assignment with very easily. Because I don't think this lecture is going to be very, very long. I'm hoping that this video will be fairly quick. Of course, it won't be if I keep going through the introduction, so let's just sort of get right into it. Before I do, though, just a couple quick announcements. When you watch this video, homework 1.1 will have been due, and so homework 1.2 will open up after this. Now, instead of that being due during the next class period, which is next Wednesday, because this lecture will go live on the 14th, and then the 17th is the Martin Luther King Jr. holiday, so class will be canceled. So instead of this being due on the 19th, I'm pushing this particular assignment back to the 24th, given all the manual issues that we've had. But you'll see when I show you the associated assignment how really easy it is. It's just meant to sort of get you used to how the manual operates. And that's really sort of the focus of this lecture, is the manual. So I want to jump right into this. Let me pull up the slide here and get right into it. Okay, so let's talk about the manual. Okay, so what is the manual? What is its purpose? What does it do for us as engineers? And so it behooves us to talk a little bit about AISC. AISC is the American Institute of Steel Construction, and in a nutshell, they are the spec and trade organization for fabricated structural steel in the United States. And a lot of the guides and specifications and whatnot that they promote and publish are sort of adopted or referenced in various codes and documents throughout the world. And they do quite a bit for the steel industry and for practicing engineers in terms of providing professional development and hosting conferences and continuing education and things like that. But one of the biggest things that they do for the industry is the production and publishing of documents for engineers, technical manuals, design guides, specifications, etc. And they produce oodles of these things. And each of them have specific purposes. For instance, they have a specific manual dedicated just to seismic design, just to seismic design and detailing of steel structures. However, arguably the most common publication, most popular publication that AISC produces is this, the AISC Steel Construction Manual. A little bit about the history, because I think this is kind of worth mentioning. It's kind of deceptive when it says the 15th edition. There actually hasn't been 15 separate editions of this manual. As we talked about on Wednesday, and I've sort of, kind of odd from a tense perspective because I'm recording this on Monday and I know what we'll have talked about on Wednesday. But in lecture 2, we discussed design philosophies and allowable stress design versus LRFD. In the production of the manual, ASD came first. So there were actually 9 editions of allowable stress design, and then when LRFD came into the picture, there were 3 LRFD manuals. So 9 plus 3 is 12. When they published the next manual, they decided to just combine ASD and LRFD all into one manual, and they called that the 13th edition. And so the 13th edition, then the 14th edition, and now we're here with the 15th edition. Because really, the actual mechanics and code specifications for steel didn't really change between ASD and LRFD. All that changed were the load factors. So it was fairly straightforward to integrate all of that into a single manual, and that's what we're still using today. Let's talk about the anatomy of the manual, because I think that the first time that you see this thing, it's kind of daunting. It's huge. There's just a lot of tables and references, and you kind of start wondering, like, where do you begin? Okay, so let's talk a little bit about the anatomy. First off, the manual is broken up into a series of parts. So if you could see me here on the camera, if you look at the manual, you will see these sort of black and silver insets, And these are breaking up each of the various parts or sections, if you will, of the manual. So there's, the first tab right here says DIM for dimensions, and then there's GEN for general properties, and then there's the beam one, and then the column one, and so on and so forth. I tend to think of the manual, however, in sort of three big chunks. So the first chunk are parts 1 and 2. Parts 1 and 2 are the two tabs that say DIM, and then the tabs that say GEN. Those are sort of the starting values for pretty much everything that we do in steel design. Those are the where you find the dimensions of rolled shapes and angles and channels and I-beams and what have you. That's where you find all of the relevant material properties. Those are sort of the starting value components. Okay, and so that's what I sort of think of as one chunk. The other chunk that I want to talk about is actually the very end, part 16. You can tell part 16 because the inset says SPEC spec. That's the specification and the commentary. Now, you could actually download the spec as a PDF online for free, and you could actually download an Excel file that contains all of the dimensions and details. So it's like, if you can download all this stuff for free, what are you paying for? You're paying for everything in the middle. And everything in the middle is really where a lot of the money is in terms of the design aids, and that's really where the bang for your buck comes from. And to be clear, there are certain components of steel design that are sort of impossible to do efficiently and economically without these design aids. In fact, for example, if you open up the FE reference manual, there are actually snippets of those design aids in the reference manual because you can't really do some of the designs without them. So they're that critical to design. Now, if you look at the numbers, I've got parts 1 through 2, parts 3 through 15, and part 16. I'm sort of avoiding part 17. Part 17 is just like a general reference. It's got SI equivalents of shapes, like some geometric formulas, math formulas, and things like that. It's just a sort of an index reference. It's not really anything super specific to what we would need to do in steel design. I want to start going through some of these sections, so I want to start with section 1. So if you're watching along with this video, I think it would be a good idea to actually open up the manual while we're going through this. So what I'm doing is I'm starting in this very first section where it says DIM, and I'm going to just one of the pages for the W shapes. It doesn't really matter what page that we're looking at here. I think that this is on page 1-18, what you're seeing here on the screen, but it doesn't really matter what page you're looking at because you see they all kind of look the same. One of the things that's noteworthy with this section of the manual are some of the schematics that are associated with these dimensions. I really think you really ought to pay attention to these. So for instance, we're looking here at the W shapes. This schematic that I have highlighted on the top left page, that visually describes a lot of the dimensions that are reported in the table. So for instance, with an I-beam, we have the flanges, which are the two top plates, and then the web, which is the middle. If you wanted to know how wide that flange is, okay, we'll go to the schematic. What does the schematic say? The width of the flange, I skipped ahead, sorry about that. The width of the flange is this term B sub F. So what I can then do is, if I'm looking at a W24 by 370, here are the terms for B sub F right there. Now, I'm sure that the first question that pops in your head is, well, wait a minute, which value do I use? Because with some of these, there are two values, okay? What you've got to keep in mind is that the steel manual is a reference for pretty much the entirety of the organization, and that includes both the engineers responsible for design as well as the drafts, those responsible for drafting where dimensions are necessary for detailing. So here's sort of an example. If I have a W27 by 129, okay, if I look at the overall depth, there are two values that I could use, either 27.6 or 27 5/8. The idea is that the 27 5/8 is accurate enough for detailing purposes, for drafting and drawing and things like that. But for design, when we're actually selecting members for the purpose of resisting loads, we want to sort of use the more exact values, or the values that we can really sort of hang our hat on in terms of capacity. So a lot of the dimensions, if you will, are going to have two values: decimal values and detailing values. The detailing values are always going to be easily identifiable, because those are the ones with like fractional values. Always only use the decimal values for computation. So if we're doing a homework assignment and you need the depth of this girder and you're using 27 5/8, that's wrong from a design standpoint. You can use 27 5/8 if you're drawing it up in AutoCAD, but the 27.6 is what you use for design, because that's the more accurate value. Now, one of the other things that I think is worth mentioning is that if you look at, let's say, my manual has all these tabs that I've placed all through it, okay? This is something that I think you ought to consider doing as the semester progresses, because there's going to be some design aids and some tables and what have you that we refer to a lot. And if you have sort of a tab or a bookmark in your manual, it makes it a lot easier to keep referring to that. Now, some students ask me, they say, well, can I look at your manual so I can just do all the tabs at once? I don't mind saying no to that, but I actually don't think it's a good idea. So for instance, during the first, like if you look at my manual, I've got tabs all over the place. But for the first exam, you aren't going to need all of these. You're only going to need a few of them. And so I don't think it's a good idea to have all of them there in place when you don't need them all, at least as we're getting started with steel design. And I'll make a habit during the semester, when there's something I think you need to tab, I'll let you know. For instance, for the rolled shapes, for the dimensions, I only have 4 tabs. I have a tab placed at the beginning of the W shapes, the C shapes, the L shapes, and the WTs. And I think for the purposes of undergraduate steel design, that's more than enough. You don't need a tab for every single permutation of shape. I think that's too much. It's too much to sift through. That's really all you need to really move forward. And then as we get later on in the semester, we'll really only be using W shapes anyway. So that's just food for thought as we move forward. Okay, design aids. So we're going to be using various design aids throughout the semester. And one of the things that you'll notice in these design aids is that a lot of them have a color scheme associated with it. Remember that we had separate manuals for ASD and LRFD. So whenever you open these design aids, be cognizant that you're looking at the right numbers. And fortunately, because it's color-coded for us, we're just looking at the blue numbers, because the blue numbers are associated with LRFD, which is going to be the design philosophy that we utilize in this course. If for some reason you wanted to use ASD, you just look up the numbers associated with ASD, and it'd be that simple. So that's just something to keep in mind. It's usually not that hard to keep track of, but just be cognizant of that. Okay, let's talk about the code and commentary. So if you remember, I had said that the manual is sort of split into 3 chunks: the component with the dimensions and details, the design aids, and then the spec. Okay, commonly engineering specifications tend to get split into 2 components: what's called a code and a commentary. In steel design, they're actually in separate sections of the document entirely. So if you look at your manual, and you'll know exactly that you're in the right spot. You'll see there's a section here in the back where the pages have this sort of gray page lining. Okay, so I'm gonna open my manual a little bit because I kind of want to illustrate the section that I'm talking about. So when it comes to the specification, what I'm talking about is sort of this component here. Let me see if I can put this in the camera here. Maybe that's a good way of looking at it. So if you notice here, I've sort of got half of the, I've got this big chunk of the manual gripped, and half of the pages are gray lined and half of them are not. Maybe I should do it like this. Maybe this is, maybe that's a good way of looking at it. So like half the pages are gray and half of them are not. The pages that are not gray are the code pages, and the pages that are gray are the commentary. Now, you'll know that you're in the specification. We'll be referring to the specification a lot throughout the semester, but this is probably one of the most important sections of the manual, is just the specification in general. You'll know you're in the right spot because you'll notice it's organized by chapters, and the chapters are organized by letter. So there's like a chapter B, chapter C, chapter D, chapter E. And each of these chapters are focused on the design or the assessment of a particular type of element in steel. So, for instance, chapter D is the design of members in tension. Chapter E, the design of members in compression. Chapter F, the design of members for flexure. Chapter J, the chapter on connections, etc. For every chapter and every section in the code, there is a corresponding chapter in the commentary. So for instance, I've got here an image on the slide. This is chapter E. This is the column chapter. This is how you assess and analyze and design columns. Let's look at section E1. So section E1 are the general provisions. This is where, for instance, the resistance factor for columns is listed. So if you're using LRFD, we use a resistance factor of 0.9 for columns, and it's delineated right there. That's what the code states. The commentary is there to explain that. So whenever there is a provision in the code, there is normally a corresponding commentary section to explain why those provisions are the way they are. Sometimes commentary sections are very, very long. Sometimes they're very short. Sometimes the reason for a code provision is very easy. Sometimes it takes a lot of explanation. As an engineer, and to be clear, we're not going to cover every single conceivable thing associated with steel design, but that's what the commentary is for. When you're out as a practicing engineer and you've got a design problem and you go to the spec, why is that the way it is? Open up the commentary. It will point you to the associated literature, the associated references that will help explain why those code provisions are the way they are. It's incredibly important to be able to understand. So yeah, there's always a code and commentary component to just about any engineering specifications. In the case of the steel manual, they're in completely different sections. A lot of specs actually have them side by side. So they'll, on the same page, they'll have the code and the commentary right next to it. Like that's how the concrete spec works. Either way, that's common in engineering specs, and you should be aware of it. All right. I do want to close this lecture with a little, so hold on, before we go into properties of structural steel, I do want to show you your homework assignment because I think that's relevant to sort of explaining a little bit about what purpose of this lecture and this assignment is. So this is going to be the homework assignment, and again, its real purpose is to just force you to open the manual. So for instance, the very first question, what is the flange width of a W30 by 292? I want you to open the manual, find the W30 by 292, and report its flange width. And so there's about 10 questions here, and then you take these questions and report the answer on Blackboard. I'm not going to ask that this be submitted until well into I think this is Monday of week 3, and again, normally I'd ask for it on I think the 19th, but I'm extending it a little bit just to give everybody time for the manual to come in and whatnot. So because I didn't want to penalize everybody here because of that. But once your manual comes in, you will find that this is an incredibly quick assignment. Again, it's just forcing you to get a little bit familiar with the manual. Okay, let's talk about steel. Now, one of the things that I think is kind of important is that you learn a little bit about how steel is produced. I don't think that it's worth taking too much of your time in this video to discuss that. I am a big fan, and I think just about every engineer I've ever met is a big fan of the show How It's Made. How It's Made has a short sort of, I think it's like a 5-minute video on modern methods for producing steel. I really think this is a good video to watch. Nowadays, at least in the construction steel market, we're not really producing much new raw steel anymore. Nowadays, what we do is we're actually melting scrap to produce steel. So we're actually recycling old steel. In fact, in the construction market, about 90% of the steel that we use these days is recycled. Now, admittedly, the construction market does not make up a large percentage of just steel in general, because really the big consumer of steel products in the world is the automotive industry. But in the construction industry, I think that we've done very good to ensure that we're using recycled materials. We're taking scrap, melting it, assessing the chemistry, and then producing new steel. And that's about how most new steel production facilities are built these days. In fact, what we're doing, there's a a new type of steel mill. They're called mini mills, where that's basically what they're doing. They're just melting scrap. That we say the word mini, but I've been to a couple of these large scale facilities. They're not many. They're pretty large. But again, where we're not melting raw or consuming raw materials to produce and cast steel. They're not as intense as, I guess you could say, as they could be. There's a couple properties about steel that I think you need to sort of like have burned into the back of your head. I think Dr. Waite would probably burn the unit weight of water in the back of your head, and I'm going to burn some properties associated with steel in the back of your head. So what I have here is the stress strain curve for steel. I am not going to turn this into a regurgitation of Engineering 216, but I do want you just to understand some basic mechanical properties of steel, that steel has an elastic range of behavior and then a plastic range of behavior. Remember, elastic behavior is defined similar to a rubber band. I take a rubber band and I apply load, it deforms. If I let that load go, it snaps back to its original position. That is elastic behavior. And the relationship between applied stresses and resulting strains in that elastic range for materials that exhibit linear behavior, that constant of proportionality is Young's modulus. So Young's modulus will tell you the relationship between applied stresses and resulting strains in the elastic range. And so the Young's modulus for steel, or the elastic modulus for steel, is 29,000 KSI. We will use that number pretty extensively, especially in column land and beam land, because we need that E property for deflection computations and for some elastic buckling stresses and whatnot. And so we will need E. We will also need the unit weight of steel, and the unit weight of structural steel is 490 pounds per cubic foot. So if I have a block of steel that's 1 foot by 1 foot by 1 foot, it will weigh 490 pounds. We will need that for weight estimations and things like that. Again, kind of a number you need burned into the back of your head. Although for a lot of structural shapes, we can sort of get around using that number because the actual weight is built into how the shapes are described. And I'll show you what I mean by that here in a little bit. Now, Young's modulus and the unit weight are independent of steel grade. In other words, whatever grade of steel that you're looking at, E is the same, gamma is the same. What changes from grades of steel are Fy and Fu. So Fy is the yield stress. That is the point at which elastic behavior essentially ceases and we start getting into that permanent deformation land. That's basically the yield stress. And then the Fu is the tensile stress, or the ultimate tensile stress. That is the maximum engineering stress that a piece of steel can experience in tension before we start getting into the necking region and before it starts fracturing. If you've had CE 321, you've probably done a tensile test on a piece of steel. You take the piece of steel and you yank on it, and right near the end, the specimen starts to neck, where the center component reduces in area, and then it fractures. And that maximum level of stress is Fu. So we tend to use the Fy limit for yielding type limits, obviously, because that's the yield stress. But Fu tends to be a valuable and easy to define limiting stress for fracture related stresses. Now, to be clear, I mean, Fu is not the end of the stress strain curve. The stress strain curve still goes a little bit beyond, and then we get fracture. But Fu is a convenient term to define that limit state, and we will see Fu pop up in some various limit states throughout the semester, and usually it's associated with fracture. Now, when you're looking at a given grade of steel, let's say A500 grade B, you need to know what is Fy and Fu, and that's what this is for. So if you go to table 2-4 on page 2-48 or table 2-5 on page 2-50, it's just the next page, this is one of the most commonly referenced guides that we use in this class. And so I have a tab for this page. I call it Fy and Fu. And this lists the material property values that we would use for a given grade of steel. So for instance, if I wanted the yield stress of A36 grade steel, it's 36 KSI. It's right there. I want to explain a couple of things about this slide and about what's going on. So number one of the things that you notice is that the manual reference is written in green. I tend to keep pretty consistent with that, if I'm referencing something in the manual, the text will typically be green and like bolded and italicized. So table 2-4, page 2-48, that's a reference in the manual. I try and be pretty consistent with that. Now, more specifically about this table, if you look at this grid on the right, you see a series of white squares, gray squares, and black squares. So the black squares correspond to preferred material specification. So for instance, if you look at the L shapes are preferred A36. And so the easiest way of understanding that is if I go to a random steel mill or a random service center and I buy some angle, it's probably going to be A36 steel. Whereas if I buy a W shape, it's probably going to be A992 steel. If you've got your manual with you, turn to the bottom of the page and you'll see that. The white is for when the material specification doesn't apply, and gray is it does apply, but you probably need to check the availability. I would just sort of assume without any further clarification that the black square associates with the shape that you're looking at. If you're designing with channels, unless otherwise stated, use A36. Now, the other thing that's worth mentioning is some of the ranges. So for instance, if you look at the range, or if you look at FU, for example, for A36 steel, you'll notice that there's a range defined. It's not, a value. It's a range between 58 to 80. Now, if you're an engineer and you need to design a tension member or a column or whatever, and you're reported a range, what value should you use for the design? Should you use the maximum value? Should you use the minimum value? Or should you use the average? Like if I have a range of 58 to 80, what should I use? And I want you to think about that a little bit. What do you think would make sense from a conservative design standpoint? The more you think about it, I think you'll realize that the most appropriate value to use is the minimum. All right. So whenever we're designing with grade 36 or with grade A36, I'm going to use an FU value of 58 KSI because I know that whatever design I produce, that it will at least that it will work, assuming that because that's the worst case scenario, right? Think if I assumed 80, or even if I assumed the average, what if I tested that piece of steel and it actually produced a range of 58 KSI, or it produced a tensile stress of 58 KSI? If I used the average or the maximum for that design, I would probably have an unsafe design because I would be assuming a stress that's larger than what the steel can actually experience. Now, I'm sure some of you are thinking, well, if there's a range, why report the range? Why not just give me a minimum value? There are specific reasons for that. I'll tell you why this range is present, and this is getting a little bit more into some advanced behavior observations in steel, but one of the things that you find in steel is that the larger the capacity, the lower the ductility. And ductility is a simple definition of ductility is how much inelastic deformation a material can absorb before it fractures. And ductility is a very desirable property with certain applications. One common place that ductility is very desirable is in seismic applications because you have a lot of energy that gets applied to buildings under an earthquake, and so we want materials that are very ductile. We don't want them to suddenly fail in a brittle mode. We want them to be able to absorb that energy. And with some materials, sometimes you get a range of behavior, and so you kind of need to understand how that might affect certain design scenarios. That's why the range is reported. So in case you were wondering, that's sort of the answer there. All right. Let's talk about the types of products that we use in structural engineering applications. And so hot rolled steel, and by hot rolled steel, I mean, actually sort of taking steel, molten steel, running it through a caster, and then back and forth through the rolling process to produce rolled shapes. Again, I would watch that how it's made video. It does a lot better job showing that process than I could. We tend to produce that steel in sort of two groups of products. So there's what I would call simple product, like flat bar, plates, round bar, and what have you, because we can take those plates and then fabricate them into a variety of elements. We can make plate girders where you actually have a plate, and a plate that forms an I-beam. We do that a lot in bridge applications when we have larger spans, because we can tailor the shape of the girder to the bridge, and that's very important when the spans get really, really high. We also need plates and whatnot for connecting elements, for like gusset plates and trusses and splice plates and connection plates. So we obviously need plates and bars to generate structural systems. But rolled shapes are things such as channels or angles or I shapes. We don't really use the term I-beams anymore. In fact, just I-shaped cross sections there are multiple types of I-shaped cross sections. For instance, the most common that we use for columns and beams and whatnot in buildings and bridges are what are called W shapes, and W stands for a wide flange section. There is another common shape that we use in applications these days are HP shapes, and HP steel shapes are meant for piles in foundations and whatnot. But they all look like eyes, but they're configured differently for different applications. Again, nowadays, so you'll very rarely, moving forward, hear me use the term I shape. I'll probably just refer to W beams or wide flange beams moving forward. I've mentioned this a few times and whatnot, but I wanted to make sure it was formally delineated. So whenever you have an I-beam, the central, here I am using an I-beam, but I'm just talking about the shape of that cross section. The central component, and this is just some terminology, is what's called the web. And then the upper and lower components, just according to this image, are what are called the flanges. Whenever you have a rolled shape, the two flanges are pretty much always the same size, but that isn't always the case with plate girders. Sometimes with a plate girder, we might have a different size top flange than we do a bottom flange. And I could talk all day long about why that's the case, about different limit states and different load demands, and why it makes sense to have differently sized flanges, but you would be watching this video for quite some time, so I'm going to move on from that. In angles, the two angle components are called legs, so if you ever hear me use the term angle leg, that's what I'm talking about. Now, and I believe this is my last slide, I just want to talk a little bit about naming. And I mentioned earlier that the weight of the cross section is sort of built into the or the weight of the section is built into the name. So I want to talk a little bit about naming conventions. So let's consider a W27 by 129. Okay, so each of those numbers means something, or each of those terms means something. So first off, the W refers to the shape classification. So there's W shapes, M shapes, C shapes, etc., WT shapes, what have you. The W refers to what type of shape it is. So if I say W27 by 129, I know I'm dealing with a wide flange cross section. Now the 27 refers to what I'll call the nominal depth. So the depth is about 27 inches. So if you were to pull all of the W27s, they're not all exactly 27 inches deep. One may be 26.8 and one might be 27.2 or 3. One might, I think, 127.6 or what have you. But the idea is that family of shapes has a nominal depth of around 27 inches. The 129 is equal to the shape's longitudinal weight. So if I was talking about a W27 by 129, it is a wide flange cross section that's about 27 inches deep, and it weighs 129 pounds per foot. So each foot of that beam weighs 129 pounds. And from a design perspective, that's pretty much all you need to know to spec out that given shape, because the W27 by 129, these are common, for example, these are common cross sections that mills are producing and service centers, house and whatnot. So it's pretty easy to refer to, and they're all unique in terms of their their designation. There's no two W27 by 129s that have different properties. So W27 by 129 is the same. For angles, the naming convention is a little different. So if I had an L6 by 4 by a half, the 6 and the 4 are just the lengths of the legs. So we might have one leg that's a different length than another. And the half is just how thick it is. And with angles, what you find is that the thicknesses actually are the fractional values. So like an L6 by 4 by a half, it actually is a ½ inch thick and whatnot. It's only with the rolled shapes like channels and W shapes and T's and whatnot that you actually need to pay attention to thicknesses being nominal versus or design versus detailing and whatnot. Those details and whatnot we will figure out as the semester progresses and whatnot. And that's pretty much all I have for this recording. Again, once you get your manual in, I would go through this lecture and I would go through this homework assignment. Again, it's very short. It's just meant to sort of make you open this manual a little bit, open it, review it, make sure that you understand how to find things, because as we start jumping into steel design, we don't want this to be a barrier. That's all I have, everybody. And since I'm pre-recording this, this will be the last lecture before the long weekend, so have a wonderful break, and we will see you when you return.